Hi everyone, my name is Lukas and today I'm here with Lena and Shiming to tell you about scaling ML workflows for real-time moderation challenges at Twitch. First of all, who we are. My name is Lukas Tencer and I'm Director of Applied Science. I lead the team. Next we have Lena Evans, who is our Applied Science Lead / PM. And then we have Shiming Ren, who is our Machine Learning Engineering Manager. But who we are as a team? Our team is called Proactive Detection, and our mission is to use machine learning to reduce harm to Twitch's users. We are part of a bigger org called Community Health. Community Health's mission is to grow Twitch by responsibly minimizing the amount of harm experienced by our community. And Community Health is part of even a bigger organization called Community, whose mission is this long thing which you see at the bottom, which is solve Twitch's highest priority customer problems / recognize highest value customer opportunities as quickly as possible, and double down on our most critical customer-oriented technologies to retain Twitch's advantage over the next decade. Okay, so on our team we do have engineering and applied science, and we really believe that engineering and applied science working together, we can get really good collaboration and help each other. But within engineering and applied science, we have focus area. First of all, production ML, where our mission is to minimize the time from business idea until the prototype is ready, or we have API already. So really speed up the model development. Then ML integrations, where our mission is to speed up the time it takes from the models ready, the API is ready, into production. And at last, once the model is in production, we want to maintain it. So our MLOps focus on building tools for maintaining these models. On the science side, we have two big focus areas, and that's content safety and account safety. On the content safety side, we want to keep the bad content out of our platform, so all the bad video, text, and stuff like this. On the account safety side, we want to keep bad users and other actors out of our platform. So the bad bots and other bad users shouldn't be there. That's it from me about the team introduction, and let me now hand it off to Lena.
Thanks, Lucas. So I'll talk a little bit about what Twitch is and the unique problems that we encounter that require us to have cutting-edge ML infra. So Twitch is an interactive live streaming service for content spanning gaming, entertainment, sports, music, and more. So streamers come on our platform to stream themselves, enjoying these hobbies, playing games, cooking, making music, all those types of things. And viewers with similar hobbies come and interact with people with shared interests and also the streamer. So if you've never seen Twitch, this is what a typical Twitch stream looks like. You have most of the screen covered by the stream. So the streamer is showing themselves playing a game or cooking music, etc. And on the right-hand side, you have a chat where users can post messages, post emotes, as you're seeing here, and they can interact with other viewers of the stream, but also with the streamer as well, because the streamer is typically reading chat. And a lot of people like to do this. Over 2.5 million people are watching at any given moment. And this manifested in over 1.3 trillion minutes watched in 2021. They're watching over 8 million unique creators streaming every month. And this results in 31 million average daily visitors. With so much usage, unfortunately, even if it's a very small percentage, some people are going to try to abuse it. And so our job is to proactively detect and prevent the abuse from happening. So what is the kind of stuff we detect? One is spam and phishing. This is generally kind of messages that are trying to get you off of Twitch and onto some other platform. And so this could be solicitation for some service, some website. Selling stuff as you're seeing here. But it could also be phishing. They're trying to get you to go to some fake site so that they can steal your credentials. We want to stop that, so we detect it and stop it from happening. Ban evasion is another example. A user gets booted off the platform. They might try to make a new account and come back. We want to make sure we know this person's bad. So if we can tie that entity back to the booted person we saw before, now we know that this new person is potentially bad as well, and we want to take appropriate action based on that. Another type of abuse we detect is usernames. You see two innocuous examples of usernames here, but you can imagine people will try to make offensive, harassing usernames that we don't want in our chat. And so that's another thing we try to detect as well. And emotes is kind of similar to usernames. Creators can submit their own emotes that can be used in their chat. And so, again, we want to prevent hateful, harassing emotes from being made. And so we proactively try to detect that so it doesn't end up in our chats. So what are the challenges in trying to solve some of these issues? One is that chat moves quickly. We need real-time models with features available real-time to find and stop these issues from appearing in chat. So think about YouTube. You would expect that if YouTube takes 2 minutes to decide whether a YouTube comment can be sent or not, that's actually not so bad because a YouTube comment lasts for a very long time. 2 minutes in the context of a very long time doesn't really matter. Whereas chat is a stream of all messages that viewers are sending. And so that means that a chat message is very fleeting. And so if we take 2 minutes to decide whether a chat message can be sent or not, the streamer could have moved on to talking about something else. The chat, other viewers could have gone and talking about something else. The message might not be relevant anymore. And that's especially bad if we're falsely kind of holding that message. And so because of that, to kind of preserve that beauty of Twitch interaction, we want to make sure that we're making these decisions quickly. Another side of this is there's a lot of chat messages being sent. The model needs to scale to handle large loads. Not only does it need to go fast, but it needs to handle large loads. Like I said, there's 31 million people watching every day. A lot of those people are chatting, and we need to make sure our systems can handle that load. On the modeling side, another issue is that most messages are legitimate. We're dealing with imbalanced data. You can imagine we'd have a pretty decent model in terms of accuracy if we just say every message is legitimate. But obviously that's not going to make our platform any safer, any less prevalent of abuse. And because of that, we need to make sure that we are choosing modeling techniques that understand this imbalanced data, and we're choosing metrics that reflect the fact that our populations are going to be imbalanced. Another factor is that bad actors are motivated. They're going to try to find ways to evade our models. This means that we need to retrain our models frequently so that we're keeping up to whatever new trends there are. But even on the modeling side, there's some stuff we can do. We can really think critically about the features we're using in our models and think, okay, is this going to be something that a bad actor can reverse engineer? Or is it going to be something that is more robust? And we really try to focus on these more robust features in modeling rather than using those ones that can be reverse engineered whenever possible. And finally, our labels are messy. We can't know 100% whether an action is legitimate or not. Like I said, a random message that we take, it's probably going to be legitimate, but we have to kind of do better than that a lot of times for modeling. And so we have to come up with models, heuristics to kind of identify good and bad populations to actually do our modeling. So now Shiming is going to talk about how we build ML Infra to address some of these challenges.
Okay, thank you, Lena. And now let's talk about how we build systems to address some of the challenges Lena just mentioned above. So most of the challenges can fall into 4 categories: scalability, reliability, reactionability, and maintainability. We will use the next few minutes to dive into their causes and our solutions. Let's first look at the architecture graph for machine learning flows in our Twitch safety world. Looking at the offline stage first, Twitch has a very powerful data lake based on S3, and we do most of our analysis using Redshift Spectrum. Spark and the Scene Axis are coming up in the near future. During our offline training, SageMaker is our core tooling. The result model can either be offline, online, or both. We do batch inference based on offline models and store the outputs in DynamoDB or our offline feature store. Online flows are a little bit more complicated. We can start with proactively scanning workers, real-time data streams, or user requests. They will be talking to online models and fetching data from feature store for real-time inference. Of course, for both offline and online pieces, we care about model monitoring and data tracking. So I added the last piece, which is monitoring, in this graph. Now, let's dive deep into the 4 categories of challenges and how this current architecture could help us leverage them. We'll start with scalability. Twitch is growing rapidly. Lena said, lots of the chat messages are being sent every day, and the number of chat messages will mostly only increase in the long term. So we need to scale up. Another reason for scaling is we are facing many unpredictable adversaries. Problems could always come back in larger scale, more rapidly attack rates, or very different patterns. In order to handle increasing data scale, we built our feature store. It is designed for performance optimization because its NoSQL nature makes it highly available, scalable, and performant. It also facilitates feature sharing and reusing between machine learning teams. It greatly reduces duplicate feature building work to meet Twitch growth pace. But we are still encountering offline data loading problems due to large data scale and how frequently data changes. Let's do a math first. We have 10 million records to load every 3 hours. In order to keep data freshness, our load needs to finish in 10 minutes. If we rely on DynamoDB batch write function, one DynamoDB write unit is capped to 1 KB. So approximately 16,000 write capacity will be needed per sec, which ends up with over $50,000 per month. So our feature store with DynamoDB is too costly, and this is not good. In order to solve this problem, we developed a special storage backend for handling these needs behind the feature store. It is our batch loading offline key service, and we call it Blocks internally. Blocks is a memory database hosted on ECS, supporting JSON line-spaced files. It could load around 180 million records in about 40 minutes with much lower cost. Blocks is fast and cost-effective in batch loading, but also provide very low latency feature serving to satisfy Twitch real-time machine learning needs. So after discussing our scalability piece, let's check out the reliability. Recall a previous challenge. Chat and evaders move really quickly, so we need real-time models and features. Reactionability represents the needs for real-time needs. It is crucial to the safety world because things are moving really fast. And there are always sudden incidents with high severity that we have to take actions very fast. It comes in 2 aspects. Can we actually react in real time? And can we bring up a new solution in short time? I would like to introduce 2 solutions we built. First, we have streaming pipeline to generate streaming features and serve them to the real-time models. Thus, we can catch most recent trends with acceptable data freshness. It is built with Kinesis data streams, Lambda, DynamoDB, and that's it. So another solution we have is Inference Gateway, because online inference is the key to real-time. It serves and manages most of our online models. It is TERP-based, where TERP is our Twitch RPC framework for Golang backend. Inference Gateway also serves as a SageMaker online model router, where SageMaker is our AWS machine learning platform. Plus, it is equipped with common libraries and key functionalities, such as feature logging. It also shortens our dev time by automatically generating model-serving APIs based on model registry metadata. That is pretty awesome. Okay, so third, let's talk about maintainability. Twitch is growing, so we definitely need something to get machine learning solutions well maintained and managed. For maintainability, we built Conductor, which is a machine learning orchestration system based on Airflow. And it manages all our science pipelines and achieves full CI/CD for the dev process. It also aims to make scientists' experience smoother by providing many pre-built components. And last but not least, it's now becoming the bridge in Twitch machine learning ecosystem. We're trying to make it the centerpiece of Twitch ecosystem by connecting model registry, feature store, data lake, model deployer, and all the other key components together. After discussing maintainability, let's touch reliability. We are a safety team. We want to be the guardian of Twitch 24/7. We're planning to invest 2 pieces contributing to reliability. The first one is feature logging. It will be helping us monitor feature anomaly and also provide good data foundation for future research and result analysis. The second piece is continuous monitoring. It can help us proactively oversee models to avoid things falling apart silently. I hope my sharing could help you understand how we, Twitch Safety Machine Learning team, conquer challenges. So to sum up, I put a full architecture graph here. We aim to build scalable and very fast reaction machine learning solutions at Twitch and provide reliability and maintainability through MLOps solutions. And meanwhile, we always take scientist self-service as our top priority to boost the overall efficiency. We are reaching the end of the presentation, and we really appreciate your stay with us for the past few minutes. We are now hiring junior to senior level applied scientists and machine learning engineers. You could check our opportunities at Twitch Career Portal. And thank you very much.